Looks at levers and the calculations associated with them. And this is our basic lever here with our pivot point known as the fulcrum, and we've got an effort coming in here which is going to lift a load here. We've got three different types or orders of levers. So then we've got our first order, second order and third order. Now the name of the lever depends on where what is in the middle there. So if you look there in the first order, we've got the fulcrum in the middle, and we press down here to lift this. So this is like a pair of scissors or like cutters. There's our pivot point there. We put the effort in there and the load is cut there or crimped or whatever. Second order lever, the load is in the middle. So if we look here, this is a table saw. We've got the pivot point here, we put the effort in here, and the load is cut there. So the load is in the middle. This is also like a wheelbarrow, so if you imagine that's the pivot point, that's where we lift it up, and that's the contents of the wheelbarrow. The third order, we've got the effort in the middle. So the fulcrum is on the end, the load is at the other end, and we put the effort in the middle. So a stapler, we've got the pivot there, we've got the load there, and then we put the effort in the middle there. This is another type of lever, a compound lever. So it's basically, in this one we've got two levers connected together by this piece here. So an effort in here on this fulcrum will lift this here, and then that will lift on this fulcrum here, will lift the load up. So a scissor lift would be an example of this compound lever. In terms of calculations, the turning force here by this load is its newtons here 200 times the distance there. So force times distance. So that would give us 400 Newton meters. So if we wanted to balance this, we would have to put in 400 Newton meters here. Now, as this is the same distance, 2 meters, obviously this effort is going to be 200 newtons. If we were to go closer, say to 1 meter, we would have to put 400 newtons of effort in. We'd have to put more effort in because it's closer to the fulcrum. If we were able to extend this to say 4 meters, then we'd only have to put 100 newtons in. So it would be easier to balance it if that lever on that side was longer. So let's have a look at this calculation here. We've got 200 newtons that's at a distance of 1 meter from the fulcrum, and we're going to put our effort in 3 meters away from that fulcrum. So logic should tell you that this is going to be easier to do because this is longer, so it's going to require less than this 200 meters. And let's have a look. It's going to be a ratio of these distances. So the turning force here is going to be 200 times the 1 meter. So the 200 newtons times 1 gives us 200 Newton meters. Now we need 200 Newton meters on this side. To get 200 Newton meters, if we divide by the 3, so 200 divided by 3, we will get the effort that's needed to be put in here. So there's our 200 is our effort that we're trying to find, times 3. So if we want to find this one on its own, we take this 3 to the other side and divide. There it is, 200 divided by 3, and that gives us 66.7 newtons. So that 66.7 newtons there, at a distance of 3 meters, would balance that load. This is another one where we're going to move the load through a certain distance. So we're going to move 500 newtons for a distance of 0.2 meters. So we're going to apply effort here, and we're going to lift this up 0.2 meters. And we're going to calculate the work done, or the energy used. Now the energy is force times distance. So our force is 500, our distance is the 0.2 that we move it, and that tells us that we need 100 joules of energy. Now we looked earlier at power and energy. So power is the rate of doing that work. So there's our work or our energy used up, and there's the time that it takes. So let's have a look at a calculation. We've got 200 newtons meters. It's moved by a lever. 100 joules of work is done, and it takes 2 seconds to lift the load. Calculate the power. So the power is the energy, which is our 100 joules, divided by the time in seconds. So it's 2. So 100 divided by 2 gives us 50 watts. So we would use 50 watts of power to lift that 200 newtons in 2 seconds. If the energy gained by the load is 90 joules, calculate the power output from the lever. So now we're going to do a bit of transposition. We want to find the power. So the energy is 90, the time is 2, so the power is energy over time. So we've got 90 divided by 2 gives us 45 watts. Efficiency, we know, is the ratio of output over input, so how much output you get from the machine to how much you have to put in, times 100%. So this example here, we've put an input of 200 watts and we've only got 190 watts out because of the inefficiencies of the machine. So what's the efficiency? The efficiency is the power out divided by the power in times 100. 190 over 200 times 100 gives us 95%. So the machine is 95% efficient.